Okay, so up until now we have studied, we saw lots of dynamic programming algorithm over graphs of bounded tree width. We will not see explicit dynamic programming algorithm today, but we'll see, at least I will mention some of the known results about graphs of bounded tree width. So what we did yesterday is that we made for minimum weight independent set, we gave 2 power k algorithm, like I'm ignoring polynomial factors. Sorry, max weight independent set, min weight dominant, a 4 power k algorithm. And for Steiner tree, we keep our big O of k algorithm. Okay. And so what I'm going to talk about a little bit is that, so these were explicit dynamic programming algorithm which we made. But there are ways to check whether a problem is FPT. So what do these imply? These imply that minimum weight vertex cover, max weight vertex cover, min weight dominating set, Steiner tree are FPT parameterized by tree width, right? This is exactly what these results imply, right? So if that is all that we needed to know whether a problem is FPT or hard, there is a theory which lets you decide it is in FPT bit more conveniently. Okay, that may not give you the best running time of the algorithm, but at least it will help you classify these objects, and then you can do your dynamic programming to optimize the constants. Okay, so we need a language. So like now we are moving towards what I call meta theorems, like where what I mean by meta theorems is that this is a theorem which has far many more corollaries than we can expect, right? So in one theorem, it captures the essence of several other problems in itself. And so to express meta theorems, we need some language, right? Certain expressibility. And some such languages generally come from logic. So one logic which I will talk about today is called extended monadic second order logic. Monadic second order logic. Okay, extended monadic second order logic. Okay, so what is this logic? So of course it has a logical connectives like or, and, not, right, implies, not equal to, okay, equal to, right? So you have such logical connectives. Okay, you have a quantifiers. Okay, you have quantifiers over what? Over like quantifiers, like what is quantifiers? They exist for all over edge and vertex subsets. Okay, so you have a quantifier over all these objects. Then you have predicate, okay, which can tell you there's a adjacent UV, right? Which basically tells you whether U and V are adjacent or not. Okay, and this is true when U and V are adjacent. Okay, and you also have a predicate which is called incident V comma E, okay, or incident E comma V. Okay, and when it is true, if V is one of the endpoint of the edge E. Okay, edge E is incident to a vertex, okay, V. Okay, so let me write down over what do you call, over edge, not subsets, over edge vertex variables, okay. So there exists an edge with this property that exists, right? But you also have quantifiers over what is that called? Over a quantifier for there exist over edge and vertex variables. Okay, and finally you can also have predicate, element, subset, okay, for vertex edge sets, okay. For vertex edge sets. Okay. So this is your language, okay. So you have connectives, you have some quantifier over edge or vertex or quantifier over edge or vertex subset, and few predicates. And what are these predicates? Whether two things are adjacent or not, something is incident to a vertex, something is incident to an edge or not, okay. So write down an example formula for you, okay, and let's see if you can identify what this is, okay. So I'm saying there exists C subset of V, right? So I have a graph over which, so this is defined over a graph, right? So there exists C subset of V, okay? Okay. V is my variable set, okay? So what I'm saying, for all V, okay, for all V in C, there exists U1, U2, okay? For all V in C, there exists U1, U2 in C. U1 is not equal to U2, so U1, U2 are two different guys because I can use not equal to, right? I can use, yes, not equal to. And what else I'm saying, okay? And what else is true? Adjacent U1 is true and adjacent U2 is true, okay? Okay, is true. That's it. So when is this true? So if this is my formula, and so this is just a formula, okay? And so suppose this is equal to phi, okay? Okay. Now we will say that G, some graph, models phi, this formula, if I can find, like in a very vague way, I can find a subset in VG such that these properties are satisfied, okay? Then I will say G models phi, right? So which graphs G will model phi, right? So the question will be given a formula. So this is a fixed formula. My input, so my model checking phi. So input is G, okay, and parameter we'll worry about later. And the question is, does G models phi, right? So when will G model phi? When G is a cycle, not G is a cycle graph, okay? Because all it says there exists C subset of V for which, so there exists a C, there is a vertex set, so that for every vertex I can find two guys U1, U2 such that U1 is not equal to U2 and V is adjacent to U1, V, and this is true about everybody else, right? So this actually represents, contains a, will model this formula, okay, or satisfy this formula. Okay? Okay. So what is Courcelle's theorem tells us? So this is just, I don't know why these pens are not working. Okay, what does Courcelle's theorem tells you? That if a graph property can be expressed, okay, can be expressed in extended monadic second order logic, then for every w, okay, greater than equal, then for every fixed w greater than equal to 1, where w is a tree width of a graph, okay, okay, there is a linear time algorithm, there is a linear time algorithm, then there is a linear time algorithm to test, for testing this property, over graphs of tree width at most w. Tree width at most w. Okay? Right? So what does this imply? If we can express some property in this logic, right, then it immediately implies that the problem is FPT, because dependence on W could be very bad. Okay? So what does it say? It never tells you, so this is all that it says, that if a graph property can be expressed in extended monadic second order logic, then for every fixed W greater than or equal to 1, there is a linear time algorithm for testing this property over graphs of tree width at most W. Right? So if I can express my property as extended monadic second order logic, then this happens. Right? So for testing whether a graph contains a cycle or not is FPT parameter by tree width, because we just wrote down a formula for this. Okay. Can we write 3 coloring and Hamiltonian cycles in AEM or so? Okay. Can we write, say, 3 coloring or Hamiltonian cycle in extended monadic second order logic? Right? So how will I write three coloring? I'll say there exists C1, C2, C3, right? So I can think of 3 coloring as a partition of my vertex set. Okay, there exists C1, C2, C3 such that for all V in V, okay, there exists I such that V is in Ci, okay, and what else? V is not in, okay, V is not in Cj, J not equal to I. So up until now, all I have expressed that this is a partition of vertex set. That's all that I have expressed, nothing more. But I also have to express independence. Okay? So how do, now I have to check, right? So what should I say? Look, so first of all, or I can write, let me write it more mathematical so that it looks, so there exists C1, C2, C3, okay, subset of V, okay, such that what happens for all V in V, this is true, for all V in V, what is true? For all V in V, V is in V1 or is this, and this is, or V is in C1, V is in C2 or V is in C3. I'll tell you why this is enough. Okay, so this much I have written, and what else, right? And what is true? For all uv in V, okay? For all uv in V, adjacent uv, so it means u and v are adjacent in my graph, then what should I say? Then what should be true? Huh? Okay. So u is in C1 and V is in C1, this shouldn't be true, so complement. And what should happen? Same with this, right? And u is in C2 and V is in C2, shouldn't happen. And shouldn't happen. Is this enough? Huh? I didn't enforce partition. All I said, look, there's some C1, C2, C3, right? And what it says, I don't care. I have covered my graph. This all tells that I have covered my graph with 3 independent sets. Then clearly given, if you can cover your whole vertex set with 3 independent sets, then you take first, right? The remaining, like, so you take first C1, next you take C2 minus C1, and next you take C3 minus C1 union C2. That's your 3 coloring, right? So even if I can cover my graph with 3 independent sets, that implies 3 coloring, okay? How will you write Hamiltonian cycle? Okay, this is a bit, okay, so let's write. Okay, so I will use some macros. So this is look, these are like your programming languages. So I'm writing a programming language, right? So I can write under some macro, and for every macro I can write it. Okay, so what is? So first, there exists H subset of E. So I have found some subset of it. What should be this? I will define what I mean. First of all, H is spanning, so it spans, what by this I will mean it spans every vertex. And for all V in H, what should be true? And for all V in V, what should I make it true? I will write another macro, degree of V in H should be how much? 2. Okay, so I will write 2. So first of all, it's a spanning, and for every V in V, degree of V in H is 2. But I have not told you how to write these things, and these are macros, which I will tell you how to write. So if I can write this, then I will be done. Okay, so first let's write down how will we write this. Okay, so what? First let's write degree 0 V comma H. How will we write this? So I want to say that, why am I writing? I can write H comma V. So how do I want to say that? If I wanted to say U has some non-negative degree, then what will say? There exists E in H such that we have a macro about adjacency, edge adjacency, right? Incident E comma V should be true, right? So there exists E in H and incidence E comma V is true. So if I want that this degree is 0, then what should be true? Not of this should be true. Right? There exists E in H, incident of EV is true. I want not, then that implies degree of V in H is 0. And how will you write degree of 1 in V. So first of all, this shouldn't be true. That will mean the degree is at least 1. So degree 0 h comma v, not of this should be true. So degree is at least 1, and something else should be true. What should be true? So how? So look, if it was incident to one edge, what did you say? Like if I wanted to say that it is degree is 0, what do you say? It is not incident to two things, right? So if I want to say that he is incident to two things, what will you say? You will say there exist E1, E2, right? And what is true? Incidence of E1 V is true, and incidence of E2 comma V is true. And what should I took? Complement of it, not of this, right? Okay, but we have to be a bit more careful. So we should write in H, E1 is not equal to E2, and this is true, and this is true, because if they are same edge, you picked up, then what will happen? Okay, so now you can also write degree 2 HV, right? So now you can also write degree 2 HV, right? This is not true, this is not true, and 3 is not true. Okay, so you can write degree 2 HV, right? You will write there exist E1, E2, E3 in H. E1 is not equal to E2, not and E3. Like E1 is not equal to E2, and E2 is not equal to E3. E3 like none of them are equal, and incidence is not true. So you can write that. Okay, so the way I wrote 0 and 1, you can also write degree 2H. It will be longer formula, but you can write it. Now, how will I write a spanning H? How do we write spanning of H? This is easy. For all UV, right? For all UV in V, for all UV in V, there exists P subset of H. For all U comma V in V. So what I'm think of this way. Suppose I had a cycle. So I can orient it in a way such that I can assign to every vertex an edge. Right? So for every UV in V, there exists P subset of H. What should I write for all? So how do we say that something has for all V in P, there exists P subset of H. Okay. For all X in what else we wrote here? What did I write here? Let me see. There exists P subset of H such that for all X in V, okay, for all X in V, X is not equal to I and X is not equal to V, okay. So these two things are true, okay, and or X equal to V. This is some moronic thing. X equal to U and X equal to V, and what should I say? Degree of Wait. Don't. I have an issue with formulas, so just have patience, okay? This is some bracket issues which is creating me trouble. For all x in V, this is true, and degree of 1 this is true, okay. This bracket is closed for this, okay. So this is just 1, or okay, this is fine now, or x is not equal to u and x is not equal to v, x is not equal to u, x is not equal to v, and degree of 0 p comma x is true, or this should be fine. Okay. So what is this tells us? For every u v in V, there exists P subset of H, P subset of H. So for every x in V, what happens? Either this x so what is the definition of spanning, right? I want to say that every vertex is associated with, like, is part of my subgraph, like is part of this some subgraph. So what I am saying, you take any uv in V, so you have picked up two vertices uv, right? So and then I will give you some subset of edges. So for every x in V, okay, either x equal to u and x equal to V, right? So for all x in V, so what happens? Either what happened is that you can assign x, like x has been assigned to same both u and V, then what happens? Then what is the degree of x in P is 1, or if suppose x is not equal to u, right, and x is not equal to V, then degree of x in P is 0 or degree of x in P is 2. This is what I want to say.
Can't we say this instead of this big one? For all V in V, there exists a E in H such that it's incident. We have the incident predicate. So incident of
Now, how does that imply that it's connected?
No, this is talking about connected. For spanning, what she says is fine.
Yes.
spanning. That is what we want.
No, we also want it to be connected, right? Look, otherwise I can also get cycle covers, right?
Yeah, okay. So you said it's all about spanning. Spanning, that's easy, right?
Yes.
Every V, you have some edges.
Right. So this
connectivity.
yes. Okay. So this is, so I also have to make sure the things are connected, right? Otherwise, this, because this will tell you that okay, every vertex has degree 2. So this is set of cycles, right? but by spanning I meant that it also spans every vertex and it has to be connected, right. So what is this trying to model is that whatever H you have got is connected, that's all, because this already guarantees you that every vertex has degree 2. So that is definitely a cycle. All I need to guarantee that whatever set of edges I have is connected. So this is basically a connectivity predicate.
For connectivity, why can't you say for every subset of vertices,
Okay.
there is an edge in H with one endpoint in the set and one endpoint outside the set?
Maybe we can say that.
Can you express this in language?
So what at least this tried to express, that if you look at any P subset of H, then for every vertex, for every X in V, I mean if P is like either you have a degree 1, like so imagine that I have U and V here, okay. So I picked up some 2 vertex in V, and so I will find this P subset of H, said for every X in V, so this is trying to model this. If X is not equal to U and X is not equal to V, then either this is true that X has degree 0 in this in P which you have selected, or X has degree 2 in the P you have selected. But maybe you are right, one can just write for every V, for every, maybe you can write connectivity that way also. We don't have to write this way. No, but maybe you're right. So all we can say is that all I needed from a spanning is connectivity.
Can you say for all subsets?
No, yeah, that's fine. No.
In this language, can you say that?
Yes, because you are allowed quantifiers. So all you need to say,
Any quantifier, not just existence.
no, for any quantifier. Okay. So yeah, you are right. Maybe I could write here. Let me try to write spanning of H. Okay. Maybe this is a bit more confusing than this. Okay. So what I will say is that for all y subset of V, what is true? So for every y subset of V, I have y here, I have V minus y here. All I need to show there exists an edge. Okay. Okay. So I have to show there exists U comma V, there exists okay, there exists U comma V, U is in Y, okay, V is not in Y, okay, and V, yeah, so there exists U comma V, U is in Y, V is not in Y, okay, this is true, and incident,
Or adjacent UV in H.
yeah, so do we what, okay, and adjacent UV in H. Okay, so let's try to write it down in this language. Okay. Yeah, I mean this will be a mess, but let's try to write it. Right? So all I want to say that exists u in y and v not in y, okay, that exists u in y, there exists v in not in y, okay, implies that there exists E in H, okay. So I have found an edge in H, and I want to say so what I want to say, if I have y, so look, this just tells you that this partition is non-trivial. That's all that it says you. And if I have a non-trivial partition, then I want to say there exists an edge which has one endpoint here and one endpoint here. This is what I want to say, right? So there exists. So if I have a non-trivial partition, then there exists E in H, okay. There exists U in E in H. There exists U in Y, okay. There exists U in Y. There exists V not in Y, okay. And what is this? Incident E comma U and incident E comma V. Okay. So we can write this. Fine. Okay. So you can also write this. Okay, this is a bit more intuitive. Okay. So if I have a non-trivial partition, then there exists an edge which is going across. Fine. So now, what does this imply? So here is a fixed formula. Okay. So if a graph property can be expressed in EMSO, then for every fixed W. So now what we know that what do you call Hamiltonian cycle parameterized by tree width as f of W times n algorithm. This is what it tells us. But so up until now, notice that a property was there such that we could describe this property as a single formula, right? But we may not be able to describe this property for a single formula, but we may be able to describe this property for each value of the parameter. Okay, for example, if I say having a set I want to test whether the graph has cycle exactly equal to. I don't know how to write a formula, a single formula, but for every k I can write a formula. What I say, there exists V1, V2, Vk, and write down all this adjacency, right? Vk in V, adjacent, V1, V2 is true, and blah, 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 right? But notice this formula has length k. So bigger and bigger size cycle I want, the length of the formula will be bigger and bigger. So actually the running time of this algorithm is not f of W times n, actually this is f of size of the formula times W times n. But if I can express formula by just single formula, then this is a constant, so you just ignore it. But if my length of the formula starts depending on k, then k will start appearing here. For example, if I wanted to test whether there exists a vertex cover of size k or not in a graph, right, on a graph of bounded, then I could have written, right, there exists V1, V2, Vk with this property. Okay. So this is like, so now problem is FPT parameterized by both k and the tree width. Okay. So problem is FPT here parameterized by both this plus W. But yesterday we were doing minimum weight, maximum weight, right? So actually what you can actually do, I'm not going, you can check the book, is that you can actually make this theorem a bit more, it was proved by other set of people, bit more, you can extend it a bit more. And what you can say, for example, I can say a property, I can do min max counting. So for example, if I wanted to write minimum vertex cover, what I can say minimize x subset of v mod x. Okay, so this is a like mod x. Now all I want to check whether x is a vertex cover or not. So but this I can test by writing a single formula. What is that? For all edge in E, for all E in E, right? What should I say? For all edge in E, there exists U in V such that incident E U. That's it, right? But now notice this is a constant length formula. This is not. This is a formula which does not depend on the size. It finds the minimum set X which satisfies so similarly I could write minimum dominating set. How will I write minimum dominating set? I could write minimum X subset of V, like minimize X subset of V such that for all V in V there exists U in, I should not be written, there exists U in X. There exists U in X, and what is true? Adjacent. So no, either there exists U, okay, for all V in V, okay. What is true? It could be true that V is in X, right? This could be true, or right, or there exists U, and what is true? Adjacent U comma V, right? So again, this is a small formula, right? How will you write if I want to write vertex disjoint cycles? I want to write maximum vertex disjoint cycles as a constant length formula. Can you write it? So what I want to write, I have a graph G, I want to write maximum vertex disjoint cycles. Okay. So how will I do? So here's a small trick which you can do. So you do max X subset of V for cardinality. Okay. Okay. So basically what I want to do, so here's my cycles. Suppose there are vertex disjoint cycles. Okay. From every one of them I have picked up one element. Okay. And what I want, for every X in X, okay, there exists Cx subset of V. Okay. Next what I should say, Cx is a cycle. This I can do. I have told you how to write cycles by now, right? I mean, for every year, it is connected. I told you how to write connected. C is connected, and how. So this is. But now, what else do I know, right? For all X, there exists Cx of Cx a cycle, and for all X, Y in X, Cx intersection Cy is empty. Right? So for every vertex in X, I have associated a set which forms a cycle. And what is the property of these sets? They are pairwise disjoint. But this is a single formula. Although, I mean, like, it doesn't look, it is not describing the cycles per se, right? But this is a very succinct way of writing vertex disjoint cycle packing. Okay? What does this imply? This implies that I can solve. So now, so even this min, max, all these kind of optimization versions of the problem, if this predicate is constant size, you can still solve the problem in f of w time. Or even if you can solve in, say, f of phi comma w, great, right? Because this is constant. Length of this formula is constant. Hello. Okay, you got medicine, sir? Oh. Oh. Okay, I will ask him, sir. Okay. Thank you. Okay. So
How is CX and CY defined as symmetric?
look, for every x in X, there exists Cx subset of V. Right? So for every vertex in X, I have defined a subset of vertices. And then you make sure this is a cycle, that you know how to make sure this cycle. And what else do you want? For two vertices X and Y in your vertex set which you have chosen, the corresponding Cx and Ci should be disjoint.
Two vertices can be associated with the same set.
No, but I don't want that. That's my whole point, right? If I want to maximize, how do I maximize? Right? I want, this is my formula. So what can satisfy this? Only vertex disjoint cycles can satisfy this property.
So if you take two vertices of the same cycle,
Yes.
what is the cycle associated with them? The same cycle.
You will associate the same cycle probably.
But
Then this predicate will not be true. You are not allowed to associate that. I want to find set of vertices for which I can associate a disjoint set of vertices. That's my goal. It's me who is going to associate, right? So I am demanding that for every vertex in X which you choose, you associate a set such that those sets are pairwise vertex disjoint. So the only sets which can satisfy these properties are which are pairwise disjoint. So for every vertex in X, you have to associate. So I will not, so all I'm saying, please don't pick two things from here because they are useless for you, right? So you pick one vertex from each of these guys. So suppose if I write this formula, which sets can satisfy? For every vertex, you have to associate different sets. Otherwise, it is just not true. So this is why we can also do.
so your X would be the set of those vertices.
My Cx will be.
No, X is the same.
X will be, yeah. Just pick one vertex from each of these. That's it. So X is one vertex from each of these cycles. That's it. Right? So you want to maximize this set as much as you can. Right? So, I mean, it's a bit clever than it appears. Okay. So even if you do min, max, all this, but the reason why I'm not stating the theorem as such, because then I have to say what is free variable and this and that. But for all practical purposes, if you can write a formula like min, max with the things which you want to verify in this language, you can still do those things in f of size of whatever formula you have and this. Okay. Okay. So good. So now I will take a detour from here and I will do something bit different. Still, we are still on tree width, but we will do very different set of things. Okay. Any question? So like this is all that I wanted to tell you about tree width, and now I will not talk about tree width. At least straightforward, like I'm making a DP algorithm unless we reach the second half. Okay, so I would like to rub all this. Okay. No. Predicate is this, like the property which you want to satisfy. Then you have to say there exists x1, x2, x3, x4, x5, xk.
So when you add this max and min, what is the name of the language?
There is no name. This is basically like associating some sort of free variables. Like there's a free variable which you want to optimize over, which is this. So like some quantifier free something something, but there is no language. Language is what you are able to write the properties. So like counting monodic secondary logic, that's different. Where I just have counting predicate here. I can count set mod some fixed p. So if I wanted to say count all sets modulo 2, right? So we still remain, okay, so let me write down an algorithm which we wrote down long time back, okay. So
Can you write this min-max as it is?
as it is. Nobody read the book, so what can I do? Okay, so I'm going back to feedback vertex set, okay. Okay, and I'm writing an algorithm for feedback vertex set, okay. So what is my algorithm for feedback vertex set? S is not equal to file, while, okay, S is not a FVS, like meaning you check whether, okay, pick random UV in EG, okay, pick random vertex, okay, X in UV, okay, add X to S, okay, and output S. Okay, so algorithm runs in time how much? If you notice, algorithms runs in time size mod S times some n plus m, okay, because all it is doing is picking some edge at random, picking some vertex at random, checking where it is. And what, but let's write down what is the success probability of this algorithm. Okay, so I'm assuming a lemma which just tell the following. So let's, okay, so let me write down this lemma which I want, which will prove it later. Okay. Lemma. Okay. Let G be a graph. Okay. Let G be a graph. S be a FVS of G. Okay. Let U comma V in EG be a random edge of edge, be a random edge of G, okay. Then with probability at least half, okay, at least one of U comma V is in S, okay. Suppose I have this lemma for now, okay. Then what is the success probability of this algorithm? Right? So you're picking a random UV in edge, right? So what is the probability? So what this says be a random edge, then with probability at least half one of these guys. So pick a random edge. So with probability half, what is the right? Has, so how should I write? Okay, so has one endpoint in opt with probability at least half. This is what my lemma tells me. We'll worry about, yes?
Don't you need to do some reduction, like picking one?
Leave that on me, no? I'm just, this is my lemma, right? So if this is my lemma, let's assume for a moment, right? I didn't give you a proof for the lemma. Okay, okay, and then what happens? So then pick a then this is in opt with probability another half, right? Greater than equal to half, greater. So what happens here? Cardinality of opt decreases by 1 with probability how much? At least 1/4. Okay? So you want to succeed if k is your optimum size, you want to succeed in k rounds. So the probability of success of this algorithm is 1/4 power. It is not as obvious as I'm writing. You need to do some induction and all other things to make it work. Okay? But this is the intuition and you can make it as a formal proof. Okay? But as you were saying, this is not correct lemma. Okay? This is a fake news. That this is true, right? But as we, why? Because you can take a big cycle and S is singleton, but S is a single vertex, but it is not true that if my graph itself is long cycle, then it is not true that half the edges are adjacent to this vertex, right? So we showed that, as you rightly pointed out, that of all bad things. Let G be a graph of minimum degree 3, then this lemma is definitely true, and we already proved this some time ago, maybe in the first lecture, right? We remove degree 1 and we shortcut the degree 2 vertices, right? So this is what we prove. So then basically my algorithm is clean G minus S, okay, of degree 0, 1, 2. Okay, and then this algorithm is definitely correct the way I have told. My claim is this also gives you a polynomial time 4 approximation. This same algorithm also gives you a polynomial time factor 4 approximation. Polynomial time factor 4 approximation. Do you see why? When I say factor 4 approximation, like, so in expectation, what is the size of S? It's 4 times opt. Right? Because you are succeeding in reducing S with probability 1/4 in each round. I mean, again. Right? So what happens? In each iteration, you're paying things like that, you're paying some 1 unit, and with 1/4, opt decreases by 1. Right? So decrease opt by making it 1. So in expectation, if you go over round, number of expected rounds where it will become acyclic is like 4 times opt. Okay, so this gives you a factor 4 approximation, the same algorithm. Okay, so if I want a good FPT algorithm, I have to run this algorithm 4 to the power k times, and if I do not care about an FPT algorithm, then I can just run this algorithm, and whatever comes, that's a factor 4 approximation, very high probability. Okay, so in expectation, you need 4 opt iteration before opt becomes 0, right? Because in each iteration with probability 1/4 only, you are making this opt decrease by 1. So like think of this like you need at least 4 or 5 iterations, 4 iterations before opt really decreases by 1. Okay, this is just simple. If you have done some simple randomized algorithm, this is just simple randomized analysis. Okay, but that is not, okay. We were talking about last time that a notion of planar F-deletion problem, okay? Okay, the reason why I bring it now, because we have input G, K, and your parameter is K, and the question is, does G has a set S subset of Vg such that in G minus S there is no graph in F as a minor, okay? No graph in F as a minor. So we are going to make some assumptions, okay? First of all, F contains a planar graph. That is why I'm going to call planar. Also, every graph in F is connected. Okay, every graph in F is connected. Okay, so I'm going to give you an algorithm for this problem in a minute. Okay, but notice, as I told you, right? F equal to edge is vertex cover. F equal to triangle is feedback vertex set, and in fact, there is some canonical set of problems here, okay, which are called tree with eta modulator. Okay, so FVS is like tree with one modulator. So I can define tree with eta vertex modulator. So what is my goal? What is my goal here? My goal is to delete S such that G minus S has tree width of G minus S is at most eta, right? First of all, as I told you, but why tree with eta vertex modulator is an example of planar F-deletion. Look, what you know, G minus S has tree width constant, okay, has tree width constant. And what did I tell you? It means look at all the graphs, that cannot be present in G minus S. Or let's look at this here, all graphs of tree width eta. This is all graphs of tree width eta. And what is this boundary telling us? What is this boundary? All graphs of tree width eta plus 1 and forward. Okay. Does this contain a planar graph? I can write down eta plus 1 times eta plus 1 grid here, right? So definitely this graph doesn't contain this graph as a minor. It means maybe my graph cannot contain this, my F either contains this, or like if I look at the characterization of eta, first of all, why they have a finite forbidden characterization, those things are, I'm not going to, but notice because it cannot contain a planar grid, it implies that one of the obstruction in F is actually a planar graph, because if not this, then any minor of this is still a planar graph, okay. So this is why this is an instantiation of planar F-deletion problem, okay. Now my algorithm is going to be for all this problem is this. Okay. Clean G minus S, pick random UV in AG, pick a random vertex X in UV, and add to X, output S. That's the end of the algorithm. Okay. So now let me tell you what I mean by clean G minus S. Okay. Okay, so that's the end of the algorithm. Okay, so now so this is why I was trying to define yesterday the notion of T protrusions. Okay, so what is T protrusions? So first of all, okay, let's use because we use T for tree width. So what subgraph, an induced graph, okay, R protrusion of a graph G is a vertex set X such that tree width of graph induced on X is at most R. That's the first property. And secondly, delta of X is at most R. And what is delta of X? Vertices in X that have neighbors outside X. So this is like boundary. We will also call this boundary. Okay. So for now, think of this graph. So here's your graph. Okay. So, and this is your X. Okay. I have a procedure. I will not tell you what this procedure is. So it takes G, X, K. So it's X is a protrusion. It outputs my G prime. Okay. So what is this? So input to this graph. This is something which I will not tell you. Okay. So this is called protrusion replacers. Okay. Replacers. Okay. So what is an input to protrusion replacers? It takes G comma K and an X. Okay. If X has some size greater than or equal to R prime, okay, if then it outputs G prime, K prime is less than or equal to K such that first of all vertex set of G prime is strictly less than vertex set of G, okay, and G comma K is a yes instance if and only if G prime K prime is a yes instance. Okay. So if this is this, then this will, else it just outputs G comma K. So what it tells is that if this is larger than some big constant, then I have a way, then I will give you a small graph patched up, whose solution does not change, and I will also tell you what is the value of k prime is, where k prime is less than or equal to k. So I will also tell you by how much your value has decreased. So for example, if when we do vertex cover and we have a degree 1 rule, we pick this, we drop k by 1, right? So similarly here, this objects, it takes you a graph, it takes you a protrusion, and what does it tells you? Okay, fine, here's your replacement and here's your new k value, okay? So it gives you everything in polynomial time, okay? So now I'm going to tell you that clean G minus S is like make G minus S free of R protrusion of size R prime. So every now you could have a protrusion, but it has a small constant size. So for feedback vertex set, what is my this? It's a long path, right? It's a long path. Your x is this long path. His interaction with the whole graph is via this. Is 3 with his 2, right? So if the size will be large, I can give you something smaller. Here I know what to do. I just maybe, I mean, I just put an edge between these two, but in general I don't know. So, but this procedure will do this job for you. It will make something smaller, okay? So clean G minus S will mean make it free of R protrusions of size R prime. Look, this R prime, look, I can only find this smaller replacement if it is too big, otherwise I cannot find, and I am like, so there is an upper bound which this R prime depends on size of the family, right? So it is a function of the family, okay? How big this is needs to be before I can clean it. Now why I'm, okay, so this is the notion of R protrusions, okay? Now let us, all of these things depends on, like R itself depends on F. R itself depends on F. What is R? Right? When I say R protrusion free, I mean, what is this R? I want it to be R protrusion free. So looking at the problem F, I decide what this R should be equal to. Of everything which is input. So in particular, R prime is a function of everything. Okay? Okay. So now let us try to see okay. I'm going to I will come up with a but let me like a formal definition of what I want. But let me do something. Let me prove something. Okay. So here's a lemma which I want to prove. And this will why do I expect to get such objects? Okay. Okay. There is actually linear time, or let's say polynomial time algorithm that given n vertex graph G, x subset of Vg, tree width of G minus x is say at most some d, okay? Outputs are 2d plus 1. Outputs are 2d plus 1, okay? Protrusion of G of size at least n minus mod x divided by 4 times neighborhood of x plus 1, okay? And d is some constant. Okay? So let me give this proof for you. This is just graph theory. It is Nothing about logic, nothing. I mean, I'm just, so it is given to me, okay? So this, I want to show you the properties of graph of bounded. Here is my x, and here is my g minus x, okay? Okay, let me throw this, okay? Here is your x, here is your g minus x, okay? And what do you know of this? Tree width of g minus x is at most d. This much we know, okay? So g minus x has a nice tree decomposition. Tr comma f, okay? Has a nice tree decomposition Tr comma f. Let's draw them up. Hopefully I'm drawing correct picture because it should be binary tree, right? Something of this nature, okay? Now what I do, look, what is n of x? It's a neighborhood of x here. So for every vertex in x, we will do some marking procedure. And what is the marking procedure? What I'm saying? Well, let's not do anything too fancy. So for every vertex, look at his neighbors. His neighbors could be all over the place. But for every neighbor, you mark the bag which is the highest. It means look, this vertex which is closest. So among all, for every vertex in x and u, for every vertex x in x and u in neighborhood of x, what I'm saying, mark the topmost bag that contains x, right? So there are lots of bag which contains u, right? So I fixed a neighbor x and it has many neighbors here. So I fix some u and I look at which all bags u is there because it's a tree decomposition of this. Now among all this, I pick the one where it is closest to the root. This is what I mean by it. So I mark like this. 5 minutes, sir. Okay? So by this process, how many neighbors, how many vertices of this tree I would have marked? How many vertices I would have marked? At most n of x. I claim that I would have marked at most m nodes in TR. Do you agree to this? If it has m neighbors, right, I could have marked some m bags, right? Maybe less because you would have marked this. Okay. Now I do LCA closure of this. Okay. Now I do LCA closure of M. What is an LCA closure of M? Look at two marked guys. If their common ancestor, like, what is it called? Least common ancestor is not in the set, you add this to set. Okay. What is LCA closure? If for any two vertices in M, their least common ancestor is not in M, then add it to M. This is also bad. Okay. How many vertices I would have added to this? After this, after the process, what is the size of M? What is the size of M? So I started with some n of x, and now I have added this. Think of this way. First of all, in the beginning, I have these guys are like, look at these guys which are leaf for now. So what will you do? Right? So every time you will be adding at most half. Like each iteration you will be just adding at most half. Because now in the next step, maybe, because now for this pair you have taken care of them. Right? So by simple counting argument you can show the size of m will be like, I think 2m plus 1 or something, depending on how much it is. Okay? You're right, it should be just 2m, not even plus 1. Okay? You can prove this for yourself that if you do this project, you will not mark too many things. Okay. Now what I do, look, I mean, okay, so here in my example, I think this is not a good example. So if this is what my marked neighbor was, I would have added this guy, right, for example. Okay. Okay. Now delete m from TR. How many components of m we have? How many components of m we will get? Huh? No. TR is like I have marked some vertices, right? I have marked some vertices in this. So do not, it's not graph, right? It's tree. Yeah, delete those nodes. There is no notion of back. There are nodes of this tree. I deleted this. How many components will I get? Look, how many edges am I deleting first of all? Every vertex has degree. It's a binary tree, at most 2, right? Except, I mean, at most 3 maybe, right? So if I delete, how many components will I get? You can actually show that it will have at most components. It's a binary tree. It doesn't matter, it is some constant time m. Believe me, you can show it is 2. But do you agree at least it will be some constant time m? Then it will just, the constant will change. It's not of important issue. But what is the property? Look at the 2m plus 1 connected components, right? So suppose these components are C1, C2, Cl, where L is like at most 2 times m plus 1. Okay? Now what I'm going to do, I'm going to define Ci prime is union of Ci prime, what I want to say, tell you, just wait a minute. Not union. Neighborhood of Ci in T union Ci prime. So tell me how many nodes, what is the size of NTCI? I claim that for any component you have at most 2 neighbors here. Can you have 3 neighbors? Look, here is a component of tree. If it had 3 neighbors from the vertices you have deleted, what is the meaning of that? It means for this I would have added a LCA closure inside. Right? So basically what I have done now, so here are portions of graph who sees 2 bags here, 2 bags here. And notice every vertex x here can only see in these bags, the vertices of these bags. They cannot see any vertices which, if I delete these 2, look at the graph, look at, now I'm going to define a set. Okay, what is this? I'm going to define Pi. What is Pi? So Pi is basically, look at T in Ci prime f of t. So look at this set of, so I have got this component and each of these guys corresponds to vertices. Look at this guy, Pi is this. Okay. Now notice that all the vertices of x sees where? Here. Because if I delete these 2 guys, I know that none of these guys are marked here. It means all the guys which are marked here is just pushed up, because for every vertex I have marked something. So what is a tree width of Pi? First of all, Pi is completely contained inside here, right? So its tree width is at most d, and what is its boundary? Its boundary is these 2 guys, right? Because these are the only vertices which in the graph, if you look at this Pi, how it is contained. So here is your Pi, right? And here is 2 boundary, right? And all the vertices of x only sees him through here. So now, what is the property of each Pi? Each Pi is a protrusion of a 2D plus 1 protrusion. Okay. So what we have shown by doing this, that each Pi is a 2D plus 1 protrusion, or 2D plus 2 protrusion maybe, because we have, yeah, it should be 2D plus 2, no? Because if it is a tree with D, so then the back side is D plus 1, so 2D plus 2. Okay? Okay, great. So this is what, but now how many, so size of M was 2 times nx, right? So total number of component is 2 times mod M plus 1 connected component. So total number of PIs are at most how much? At most how much? 4 times n of x plus 1. Okay. So by pigeonhole principle, there exists a 2D plus 1 protrusion of size n minus mod x divided by the number of such object. Okay. So in polynomial time, if I had this set x, then I know how to find this protrusion, and I'll give you, and I have a replacer which will replace it, be done with it if it is too large. Okay, this is the whole. Next I will tell you that if you do not have this protrusion, then why this algorithm is correct.